Right. Okay, so welcome to the engineering drawing class with me for class 07. So before we start, please open your CX and then click on your presence. Uh, there should be, so now we have 22 people ready. So please, so I only open the CX up to 13:30, yeah? So um, and here there are how many people? Check, check, check. Okay, so there should be 34. Yeah, please click on your presence. Uh, the second one, we're gonna use this link for Zoom meeting. There are eight. There are only 8 weeks for the theory. Yeah, so I'm gonna giving you the theory, and another um, half semester is for the lab. Yeah, for the practicum for the SolidWorks practicum. Okay, and yeah, that's the first one. The second one, um, who is the ketua kelas? The uh, Nashua, yeah. Nashua, are you here? Right. Okay. So I will share screen to show you about the EduNext. Wait. Okay. So now we have EduNext at class 06 like this. So I would like you to just open the. So I'm gonna share the token. Yeah. Uh, this one. Where is the token? Wait, wait. Okay, so this is the tokens, the course token. So have you so please enroll to EduNext. So I'm gonna put all information to EduNext. So this is specialized for international class. Yeah, the token expired tomorrow. Okay, so I think I'm just gonna copy this one and maybe share it to you. That one. Okay. Yeah. Right. Now, okay. So please enroll in this class. So I will give the module. I will put it. One module means 1 week. So there would be 8 modules. Then it would be around 8 weeks. Yeah. For seven to 8 weeks. Okay. For today, uh, you can have a look, and then I have given the PPT or the PDF of the handout, so you can have a look to check the handout here, and so you can download it, and then you can make some changes if you want, and then if you have a tablet or uh, like pen, you can write it up. Okay, so you don't need to spend a lot of your time to rewrite what I'm saying. Okay, uh, in here there is a untitled submodule. This one I have to write it out. Yeah, I have to edit additional videos. Okay, so okay, should be. Okay, and in every week I will also add some additional videos that would be very important for you, or maybe beneficial for you to learn for each week. This gonna help you to understand the handout, the materials that I gave you in each week. Okay. So for example, for this week I have added 2 more videos, and we're gonna watch them together as well, just to make sure that yeah, we can get more ideas about this engineering drawing. Right. Okay. Before we start, I would like us to open the camera first so I can know your face, please. Please open your camera. Albert, are you now like traveling, coming to Bandung or something?
Hey, I'm just still in the car, man.
Okay. Okay, please open your camera. Right. Okay, Fidela, Andi, Talita, Ifat, Madaya, Fadil, Alexander. Right. Okay, so I see that some of you are listening through your phone. Um, some of you are already in Bandung, yeah, and some of you are still overseas. Okay, just keep healthy, and then uh, again, because I'm also your advisor, always yeah, you have to communicate with your advisor, or me, the advisor, or the kaprodi, yeah, the program chair. Okay, let me okay, so I'm gonna just put the camera. I'm gonna screenshot one and the second one. Okay. All right, everyone. Thank you. So I hope you can enjoy the lecture. You can close the camera if you want. Just close the camera. That's fine. Now, okay. So before we start, okay. So any question before we start? Okay, not yet. Okay, okay. So today I'm gonna start share screen from the materials that I gave to you in the EduNext, so you can have a look or just listen. And after this, usually I'm gonna put the recording on YouTube, and then I'm gonna put it again the link into the EduNext, so you can have some ideas, have some time to again, maybe you want to open and pause, and then maybe replay it again, yeah, right. Okay, so because this is 2 credits, yeah, 2 SKS, so that means you should spend around 2 multiply with around 3 hours per week, so around yeah, 3 hours per week, so you should spend around 6 hours per week to study about engineering drawing. Okay, let me open the maybe share screen. I'll try to open it with from others. Okay. Yeah. Okay. Yeah, I'll try to use iPad. Let's have a look. Okay, everyone. So so this is KU1267 engineering drawing. So what we're gonna learn is a really basic about engineering drawing. Yeah, in ITB in the first year is actually you're still generally you are still in a faculty in the Fakultas Teknologi Industri, but for you for international class you already know that you're gonna be in chemical engineering. However, the engineering drawing that we're gonna learn, because it should be similar with other programs, other students in FTI, so the engineering drawing that we're gonna talking about is a very general one, the one that is used with industrial engineering, mechanical engineering, or civil engineering. Yeah, so it's very general. Okay, later on you're gonna see that in chemical engineering there should be a slightly different, but yeah, we start with the basics. Okay, right. So let me start explaining about the introduction first. So I've been teaching gambar teknik, yeah, or engineering drawing for about 4 years now. So if we look at here, oops, wait, why not? Maybe I think I have to. Wait. All right. Let me stop share first, and then let's start again. Okay. Or maybe I'll just open it from here. Yeah, I think it's better. Okay. Let me share from just the laptop then. All right. Okay, I think this one's better. Okay, so now, yeah. So what we're gonna learn in technical drawing, yeah, this one, Introduction to Graphics Communication or Engineering Design Process. So the learning outcome that you're gonna learn for today is to actually to learn about the skills, or of course you have the ability. So it should be knowledge. Yeah, you have the knowledge and also you have the skill. Punya pengetahuan dan juga punya keterampilan. Okay, so the skills and ability to utilizing a technical drawing in 2-dimension and 3-dimension as a standard communication media in engineering activities. Yeah, so that is the outcome for this course. Okay, this is very basic, but of course we're gonna learn a lot of new things here. Yeah. Right, so engineering drawings, it is actually, this is for example, an example of a drawing of gears, yeah. There's a big one and also a smaller one. And then to draw this and then to make sure that others can understand what we want, the other engineer or the technician can understand what we want, is actually we have to use a technical drawing. Okay, I can give you some examples here. For example, this one, yeah. So so my husband is also a lecturer in ITB in mechanical engineering, and he last year he had a research project about a 3D printing. So he bought a 3D printers and then put it in our house, and then and then doing the printing. And then here is an example that the one a model that he want to make it for just a simple like a gearing or something. You can see it's like this. So when we maybe put it like that, yeah, and then the gear can maybe rotate something. Okay, so how he can build this one? The one that he can build this one is actually there should be someone others from the internet who make the technical drawing, and then they put it into a model, and then they can make the model is available for free, and then my husband download it and then put it into the 3D printer, and then the 3D printer will print it exactly like this one. So they print it into several parts, like the gears, the red one, the green one, and also the base, yeah, with different color, and then he combined them together. Okay, so so imagine, so we don't know, so I think the engineer who built this one should be in somewhere in Europe or in America or something, yeah, and then but they make the drawing, and then they make the model, and then we can apply it. So somewhere in Indonesia here, we can just we can download it, and then we can make this example of gearing. Yeah, another example, actually I should bring some as well. Where is it? Oh, maybe on, I think that's this one. This one also, yeah. So this one is also a typical. So hopefully, if we can have a class in the class, yeah, we have a it's like a hybrid. I can bring some of the models, and then you can have more ideas, and then touch them, and then see them like in yeah. Just directly like this. They also make the models, and then so when we rotate it, then the gear can running like that. That's the basic of machinery. Yeah. So this is just some examples that I just brought it from him. That an example of engineering drawing. Yeah. So in a sense, we there's a standard, and the standard is ASME. ASME is stands for, where is it? ASME stands for the American Society of Mechanical Engineering. So all the standard regarding the mechanics, the machines, or something, and or for the worldwide standard is ISO 8015 about geometrical product specification, fundamental concept, principles, and rules. Okay, so engineering drawing is, in a sense, is the activity that produce engineering drawings, the documents. So all the activities that produce the documents, and then those documents, we as an engineer, and you also we will be engineers to be, yeah, we should have a document that can be read by others, by other engineer or other appropriate who gonna read our work, and then they should be able to reproduce it. Okay, so more than drawing a pictures, it's actually a language. So graphical language that communicates ideas and communication from one mind to another. Okay, when I was just graduate from ITB, I work in a engineering consultant, and my job at that time is to review documents. The document is an engineering documents to build the BP Tangguh plant, the gas natural gas plant here in Papua. At that time, it hasn't been constructed, so I'm a part of the team that review the engineering documents, and those engineering documents is actually comprised of we call it PFD, PNID for chemical engineering. Okay, so I don't know who make maybe the one who make the engineering drawing should be engineer from Japan, maybe, yeah. And then me, Indonesia, as a new chemical engineers, review the diagram. Is it right? Is this equipment is good or not? We don't meet one person to one person. I don't know who made the document initially, but I can review them and then I can understand the document because we use the same standard. Okay, so because we use the graphical language that communicates ideas and information from one mind to another. Okay. Another example, for example, is in the chemical engineer, yeah? So our designers, okay? So we want to make a chemical reaction, and then with in the third year you will understand to design the chemical reaction. So of course you're gonna design the sketch and then the dimension, the thickness of the wall, the detailed parts of the elements, and then um, so we have all those ideas, yeah, in our brain. We want to know how to make we know how to make a very good equipment that is safe and good and then would be usable, yeah. But then the one who made the chemical reaction is not chemical engineer. The one who made chemical reaction would be mechanical engineer. Okay, so what we can do is actually we have to sketch, design, and detail all the elements, and after that, with the similar standard, and then gave it to the mechanical engineers, and the mechanical engineers will give it to we call it drafter, yeah. The drafter is like vocation graduate, yeah, D3, yeah, or something. So he specializes in drafting, so they're gonna draft, and then after that, we're gonna give them to the uh, to the we call it technician, technici, yeah, in the workshop, in the manufacturing workshop, and then they will build this one. Okay, so yeah, so this is, for example, this is an example of chemical reaction. This is the vessel, and then you can see there's a lot of input and output, and then here there's our tubes, yeah, because of there are some arrangement of the reactor. Okay, so we know the idea in our head or our brain like this, and then what we need to do is how to draw it very carefully and with every detail included, so it can serve as a language. Then we can communicate to the other person, for in this case, for example, for mechanical engineers. Okay, right. Okay, so this is the an example of engineering drawing of the reactor. Here is a vessel, yeah, so you can learn that this is going to be the vessel. In the middle there is an agitator or pengaduk, yeah, the agitator here. There are three steps over here, and then there are here around here would be the inlet or outlet. Okay, and then there's some smaller codes here. I think it should serve as maybe the vent, untuk mengeluarkan, ya, the vent, or maybe indicator or control. And around here is the power. The power is to rotate the agitator. Okay, so here this one is we have this technical parameters, and because it's an example, yeah, so there would be a watermark in here. So this one tells you the company who draw the reactor, Ryan, for example, blah 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 blah, Ryan Light Machinery Co. Ltd. Limited. And then here there is I think like numbers thing, and it's also there's a legend there. Okay, and then this is from the front view, yeah, the front view, and this one is from the top view. Okay, so what you are gonna learn in the next 7 to 8 weeks is how to translate, or if we have a drawing, and can we draw it. Okay, so that's an example. So engineering drawing, artistic drawing is actually a both type of drawing, and either may be called a simply drawing when the context is implicit. So engineering drawing also shares some properties with artistic drawing that both create pictures. We as a chemical engineer should also have a sense of drawing, and when we draw something, it should be with some dimension. Okay, so uh, but the artistic drawing is usually convey emotion or artistic sensitivity. Yeah, how to draw a beautiful house, how to beautiful animals, for example. But for engineering drawing, in each drawing, it will convey information and objective facts. Yeah. Okay, so because it is a language, because engineering drawing is a language, and also. Okay, I'm still mute. Good, thank you. Okay, yeah. So the engineering drawing will share some properties, and yeah, for engineering drawing only, just to we have a lot of information. Okay, let's just continue in this one. Okay, so okay, you should hear my voice, yeah. Okay, so engineering drawing, because there would be a lot of convention. What is convention? Peraturan, yeah. There would be a lot of rules in engineering drawing, up to the detail. For example, the thickness of line, it also is different. It has different impact. If you have straight line and if you have like a dash line, it actually tells you different information. Okay, so yeah, of course, engineering drawing will require some training to understand. That's why we're studying it. But there are also a high degree of objective commonality in the interpretation. Okay, so we have some convention, and those convention is actually quite similar between the American standard, between the ASME, for example, and the ISO, or maybe British standard, or Australian standard, or China standard, or Indonesian standard. Yeah, so yeah, we use quite an extensive set of convention. Right. Okay. So this is an example of graphic communication. So it is means to communicating technical ideas, a problem solution, and of course, our historian also, the historian, yeah. For example, for the Egypt history, they try to interpret the communication using the one is written here. So graphic communication using engineering drawing and models in the language, clear and also a precise language with definite rules that must be mastered if you are to be successful in engineering design. Okay. Right, this one as well, about writing, yeah, about the ancient writing from the Chinese one. So I also learned a little bit of Japanese a long time ago when I still just graduated from ITB, and then I understand the online, the woman, why it's called like, it's written like this, for example, or why the gate is written like that, or just a day, because it is actually like a symbol. Okay, so it is a very quite like years ago, yeah, about the grammatical communication. I'm sure you don't see this type of phone. Maybe you're still just born, I think, yeah, with this type of phone. But anyway, just try to think who use graphical communication. So at that time, I think it should be around 2000s, yeah, the when you were just born, or just still toddler something, yeah. Okay, so looks like I have really bad uh, link, the bad internet. So I'm gonna close my video to so I can more focus on editing this one. Okay, can you see my screen? Hello? Oh yeah. Okay. Yeah. Okay, so who use graphical communication? The 25% use 3D modeling and documentation, 19% manufacturing engineering, 23% functional design, 15% engineering analysis, and others. I'm sure now we use a lot of graphical communication. You too, yeah, using Instagram, using TikTok, using Reels, using this also part of graphical communications. And we actually now getting used to have an infogram, yeah, or infographics, yeah, in you're also used to read PowerPoints compared to read books. And our eyes is really eye-catching, yeah, to those graphic communication, and it is really easier for us to learn about about the graphics. Okay, so now let's go to the next slide. This one. Okay, so now let's start. This is actually quite simple, yeah. So this is called this is a spreadsheet, or the sheet for the type of engineering drawing. Want to understand the titles is around here. So this is the title, you can see around, just around the corner here, the hanger assembly. This is title hanger assembly, and who made this? The one that made this one is the link belt company. Okay, the link belt company, and then you have the code, and even the code also written like mirrored. So if we read it from this side, we can also understand the code for that one. Okay, now, and after that, here we have the dimension tolerance, yeah, the dimension. So we're gonna learn about the tolerance next week, about the tolerance, and also there's some codes here. Okay, if we learn about the three dimension, it would be looks like this. So they try to put the dimension here. Okay, and then this side is the tampak depan, ya, or the front side. So if we look at here from this case here, this is the around the front side. You can see there are two screw around here. There's a screw here, and the dash line here is the one inside, the part that we can't see it from outside, but the part is there, yeah, it's inside. Okay, and then this tells you the dimension. So for example, 342 something, I don't know. And then all this one also, there's NPT like that. This also a code, yeah, or a symbol like that. Okay, and then here you also have the diameter of with the 12, the dimension is a 12, for example. And then here is the drawing from the side ya, gambar tampak samping. Okay, so you can have some ideas how to draw from these sides into these sides. Okay, and then even we can actually know the types, yeah, the types, the symbol and also the type as well. For example, U bold is written with the symbol A, so this A is actually the U bold, yeah, like that one. And then B, for example, is the babbitt frame, this one. And then C is the hex nut for C. Okay, I'm sure it should be quite new for you who doesn't really like about the workshop. But I think you can start familiarize about this part. For example, when you're making your own furniture, if you just fill your kosan, yeah, your room with some furniture, maybe from IKEA or from Informa, and when you want to build the furniture by yourself, then you have to read instruction, and the instruction is written in the like this engineering drawing. So we just need to follow the step by step, and then we can make that one. Okay, so right, we can't do this here. Usually in the class, I will form groups of students, and one group will close the eyes, and one students will close the eyes, and the other students will look at to the whiteboard, and then I'm gonna show you the a schematic of some piece of materials. Okay, so in each group is actually the student number one who see uh, the 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 drawing. They will describe verbally, just saying to the friends, and based on the description, the other part, the second students will draw the part while not looking at the screen. But anyway, because you are now looking at the screen, so I can't use this quiz technique. That's fine. Yeah, okay, so for example, this one. Okay, so this is the type of the material, and then how okay, so I think I would like to invite you to try to describe this piece of material. Anyone would like to try? Can you describe the specimen? Who want to volunteer? Come on, anyone who want to volunteer, try to describe this piece of specimen. Oh, okay, yeah. Who raised hand? Yes?
I'll try.
Aska, okay. Aska, try to describe this.
Yeah. Okay, it's a piece of horizontal bar with two small holes on the right and left side. That's about 1 centimeter in length.
Yeah.
That's about 1 centimeter in length, and then in the that is about 3 centimeters in diameter, and then there's a extrusion on the front of the bar that's about like 5 millimeters in length, and then it's around, and the hump in the middle is hollow.
Right, okay. Okay, anyone would like to add? Okay, now try to imagine that we don't see the picture, but we hear Aska tell you about the specimen. Maybe I would like to invite Adlina. Adlina, are you listening? Hello, Adlina? Arfa, are you listening? Yeah, Adlina?
I'm sorry, Miss. I'm still outside.
Right. Arfa, are you listening?
Yeah, Miss.
Yeah. What do you think about Aska's description? Can you, if you don't see this picture, yeah, just close it with your hand like this, and then do you think you can draw a very accurate specimen?
Accurate? I don't think so, Miss. Maybe I can get down the horizontal bar, like the holes
Right.
on the edges, but like what am I? The middle part, like the hump or everything. I don't know. I'm kind of lost in that part.
Okay, yeah, yeah, of course, yeah. It is not about a right or wrong question, but how about you, Aska? Is it difficult to describe that one? And how do you describe, because the bar is not a sharp, right? They should be like apa rounded on the edge, yeah. So anyway, from Arfa and Aska, yeah, yeah, Aska, yeah. Hello.
Yeah.
Yeah. Uh, would you like to add something?
To the description,
Yeah.
or no? Maybe that the fact that it's round on the edge. I think that's it. I think, yeah. I mean, without proper like measurements, it's hard to describe the
That's the things, yeah. So this is actually the problem that we face is actually when we want to describe something, a specimen to other person, and then we don't know the information, like Aska said. We don't know we don't know the dimension. Oh, okay, and then also it's very hard for us to understand if we don't see the picture. Yeah, I'm also as an engineer. I'm very used to see the. I need to watch. I need to see the schematic of equipment first, especially when my students, for example, discussing about our research and so on. I just want to see. Okay, first, where is the graph? Okay, that is very important for us. Okay, so okay, so but however, if we use a technical drawing, in engineering drawing, we can actually, for like example, Aska can also draw this and then give to Arfa. Yeah, this one is from the top side, and this one, the front side. Yeah, this one is from the front side, and this one is from the top side. Okay, now try to imagine the specimen by looking at this drawing. Okay, try to imagine. So this is the front side. Yeah, this circle here, which is a line, yeah, a bold line, a straight line, and then like round, is actually a part that can be seen from the outside. Yeah, so we can see in that one. I have an example. This is a tumbler. So if I can see the edges of those circle, I can write it like that. Okay, and because if it is a circle, yeah, it's like a cylinder, it will have a center point, and then the convention will show you that, so this is the center point. Yeah, it is actually written by the line, and then there is a plus here at the center point, and then another line like that. Okay, from here, from the top side, from the top view, from the front view, tampak dari depan, we can't see anything in here. Yeah, we can't see anything. It's just like a piece of specimen, like that piece of metal. But actually, we know that there's something, a hole in it. There's something extruded in it. Yeah. Okay. So what we can write is actually, we can write a dash line, and then dash line tell you there should be some chopping or some there's something inside, but you can't see it from outside. And again, because it is a cylinder, it should have axial, yeah, punya poros axial. And this is also written by this pink line, and then a very specific long line, and then a dash, and then a long line again. Long line and a dash and a long line. And while the dash line just tell you that there is a hole in it. Okay. Then we combine it from the top view. Yeah, from the top view, here there is a tukikan, or the edges, or like something like this. So we put a straight line there, and then we know from the top there is a hole in it. Yeah, and the hole is from the top. We can see it. It looks like a circle. So because it looks like a circle, so there should be a center point. Okay, the two center points there, and then inside this hump, yeah, we can't see anything, but we know because from the top view there should be a room or a tunnel like that. So we put it like this one for the cylinder, and also the edges. Okay, so with these examples, you can now you can have I'm really sure if you're written, if you're given this 2-dimension, you should be able to draw the 3-dimension. Yeah. Do you think so? If I give you the 2-dimension, can you try to sketch the specimen here on the right side? Can you imagine?
Yes.
Yeah.
Yes, I think so, somewhat.
Yeah. Okay, Arik. Yeah. So I think usually the boys can have more a 3D knowledge or something. Yeah. But of course the girls also, you should have actually as an engineer, because we're actually architect. Yeah. We're architect for chemical plants. Yeah. So again, we still have we need to have a sense of 3D, and then the ruang, the volume like that. Okay, so rather than we explain it using verbally, it's much better if we can draw the technical drawing like this, and then give it to the technician, and the technician in a flash they can make this specimen. Okay, now any questions? No, not yet. Okay. Before we continue the with this one, let me explain about maybe I'll just share some videos. Yeah, so we don't feel very sleepy. You can also watch the video on the EduNext. So let's watch them together, so maybe you can get some more ideas about this one. Yeah. Okay, so let's around 10 minutes.
Engineering drawings are the most important deliverables that a design engineer produces. They provide all the instructions needed to make parts.
Can you hear the sounds? Yeah?
Yeah, loud and clear, miss.
Yes, miss.
Okay, good.
Engineering drawings are the most important deliverables that a design engineer produces. They provide all the instructions needed to make parts exactly as you intended. But bad drawings will make you look like a bad engineer, and parts made from them are sure to have problems. In addition, many machine shops refuse to quote jobs that have bad drawings, because nothing is more disruptive to them than having to call the engineer for missing dimensions or clarification. In this video, we're going to give you some tips for making clear, complete drawings so you don't embarrass yourself.
We tried to make this video as painless as possible, so we provided lots of extra resources on our website that cover the more tedious details. Our checklist will help ensure your drawings are complete, and this reference sheet shows some different ways to dimension common features. We've also provided a fully dimensioned drawing package with both detail and assembly prints to serve as an example. And if you really need to dive into the details, we've provided references to the relevant ASME drafting standards throughout the video.
These days, the vast majority of 2D drawings are made in the computer from a 3D parametric CAD model. In this video, we're going to be using Autodesk Inventor, but the information we're giving you applies to any software package or even hand drafting. If you're new to CAD, Fusion 360 is free for hobbyists and startups and is a great option.
We're going to be working to the drafting standards of the American Society for Mechanical Engineers, which is the default in the United States and much of Canada and Mexico. In the rest of the world, ISO standards are typically used. There are some minor differences between the standards, but a lot of the fundamental concepts we're covering in this video apply to either system. For the rest of this video, we're going to use this brake caliper assembly as an example. We'll highlight some rules, best practices, and tips for both the detail and assembly drawings, but we're not going to show placing every dimension because that would make for a very tedious video.
When making a drawing, you'll usually start with a template, which is typically the same for both detail and assembly prints. At the time of this video, the template that is built into Fusion 360 is not compliant with the ASME drawing standard. We've made our own standards compliant template for Fusion 360, which you can download from our website.
The title block gives information about the company and people responsible for the design, as well as the drawing name, number, and revision. It also specifies the sheet size and primary scale, and you'll want to choose these so that you have enough room to place all the dimensions in each view.
Within the title block, there's also a list of blanket tolerances that apply when a dimension is given on the face of the drawing without an explicit tolerance. A big problem we see with drawings are title block tolerances that are unreasonably tight. In the format we've provided, we tried to choose tolerances that are reasonable for most modern CNC machines, but you may want to increase these even more depending on the type of work you do.
The title block on subsequent sheets of the same drawing usually contains less information and is called a continuation title block. The revision table shows when the drawing was changed, for what reason, and by whom. The notes list provides information like the material and coding specifications, relevant standards needed to interpret the drawing, special instructions for manufacturing certain features, and other information that can't be conveyed with a dimension. The border defines zones with letters and numbers that allow you to identify specific features with coordinates. This is really handy on big drawings because you can say something like change the 0.19 hole diameter in zone A7 and be able to jump right to it, instead of having to scour the entire drawing to find something.
The face of the drawing will usually have 2 or more views, and they must have a particular alignment to each other. We're going to switch to hand drafting for a second to talk about where this convention comes from. To draw this example part, we're going to choose a view to be our primary or front view. But there's other features of the part like the larger tapped holes in the slot that can't be seen, so we need to create additional views around the front view that show them. To draw these projections, we have to imagine that we are rotating the part in space. If you're making drawings in the United States, you would rotate the part in this direction. This is called third angle. To detail other views, you'll project the lines from your front view to define the features. You need to make it clear in the title block which convention you are using, and that's what the cone symbol is for.
3D CAD can create problems because it allows you to very easily break the alignment and place a view wherever you want. You should really avoid this because the person reading the drawing will use the orientation of the views to reconstruct the part in 3D, and breaking the standard alignment makes this process much more confusing. It's also a great idea to drop an isometric view to help clarify things. Isometric views don't have to be strictly aligned to the orthographic views, but you should draw them in the correct corner for the orientation you want to show. You can put notes in an isometric, but you don't put any dimensions since the features don't appear in their true size or shape.
You'll usually want to show hidden lines to help depict the internal features of a part. However, having lots of hidden lines can sometimes add confusion, so you can omit some lines for clarity. This is really a case-by-case thing, and your primary objective should be to make the drawing as clear as possible. The same is true of tangent lines. You will usually omit them in orthographic views, but sometimes they're needed to make the view recognizable. You should also avoid dimensioning to hidden lines, so you will often need to create section views to dimension internal features. Smaller features often need to be shown at a larger scale, and detail views can help you do this.
With your views arranged, you can start adding dimensions. When placing dimensions, you need to fully define the size and position of every feature, and this is where new engineers typically struggle the most, so be sure to check out the reference sheet on our website. The general rule is that dimensions should be placed outside of the view. You are not allowed to cross the dimension lines with either extension lines or leaders. Round features and arcs greater than 180 degrees should be dimensioned according to their diameter, and a diameter symbol will precede the dimension. Arcs less than 180 degrees, like fillets, should be dimensioned by their radius, and a letter R should precede the dimension. There are some features you don't have to explicitly dimension. If 2 edges meet at a 90-degree angle, you don't need to place an angle dimension. It's just assumed to be 90 degrees. Similarly, edges that appear to be tangent, like fillets, are assumed to be tangent.
You cannot have multiple dimensions that conflict with each other. For example, this view of the bore cap has an overall length dimension, as well as these dimensions that define the thread length and flange thickness. These dimensions conflict, and one of the 3 is redundant. To minimize the tolerance stack, it's best to dimension it with these 2, but having the overall length is helpful, and we want to show it on the drawing. To resolve the conflict, we can place parentheses around the overall length, denoting it as a reference dimension. This means it doesn't control the part in any way, and is simply for informational purposes. It can be very helpful to provide reference dimensions that show the overall size of parts, so you can easily see the size of stock needed to make it. Threads are called out with a note that specifies the size, standard, and usually the tolerance class. You can also specify the depth in the note or with the dimension in a view. Many times, you'll have multiple instances of the same feature like these fillets. You can use a note like 2x to indicate this, or multiple liters. Sometimes people will put TYP for typical, but you should avoid doing this because it can be extremely confusing when there are multiple features that look similar but are really different. Critical features in your drawing will often require tighter tolerances than what is stated in the title block. A lot of times the tolerances will be provided to you by somebody else. For example, this hole holds a special type of hydraulic plug from the Lee company. Their technical references call out the dimensions and tolerances, so we can just copy that onto our drawing.
In an earlier video, we talked about how to use design tables to set the tolerances for the fit you need between components. For more complicated interfaces, you can use a technique called geometric dimensioning and tolerancing. GD&T is fairly complicated, and we're going to have to make multiple videos just to cover all the nuances. But until then, here's the elevator pitch. GD&T gives you a way to describe the functional requirements of features by controlling things like flatness, perpendicularity, position, and runout. When using GD&T to control a feature, the locating dimensions are typically enclosed with a box to indicate that they are basic or theoretically exact. The feature is controlled by a special node called a feature control frame, which may also reference other features as datums. If it sounds complicated now, don't worry, because we're going to break it all down into much simpler terms in future videos.
The important thing we want to emphasize is that there is a systematic way to calculate what every single tolerance should be to achieve the intended functionality. It's terrible practice to put an arbitrarily tight tolerance on a dimension just because you think it's a critical feature. You will often need to specify surface finishes in locations where you have a seal. There is a special symbol to do this. The number indicates the root mean square height of the surface in microinches, and this is inspected with a special type of instrument called a profilometer. Notes are critically important for clarifying the drawing and fully defining the part. A lot of notes will apply to the entire part or drawing. For example, you can use notes to specify things like materials or coatings. When listing material, it's critical to specify the alloy, heat treat, and material specification. Just saying something like 316L stainless is not enough because this particular stainless alloy can be made for normal industrial applications or an ultra-high purity and cleanliness for pharmaceutical and biomedical applications. You need to list a specification to clarify which version you need. You should not use notes to specify things like quantity, delivery date, or payment terms. This information will be listed in the request for quote and purchase order. Other notes will only apply to a specific feature. These are often called flag notes because a little flag symbol is sometimes used.
You typically don't want to have sharp edges on any finished parts because it presents a safety concern and burrs can interfere with components fitting together. If all you want is an edge break, best practice is not to model or dimension small chamfers or fillets. Instead, you can use a general note asking the manufacturer to remove burrs and sharp edges and perhaps only supply a loose range for the size of the edge break. If you use a note like this, you've given them the option to deburr on the machine using a hand tool, grinder, bead blast, or a vibratory finishing machine. But if you place dimensions in a view to specify the edge break, you've pretty much forced them to machine it, and it becomes a feature that has to be held to a tolerance and must be inspected.
Assembly drawings are critical for showing how complicated assemblies go together. Enough views should be chosen to clearly show every component. Parts are often identified with a find number in a bubble. A parts list on the face of the drawing indicates the corresponding part number, description, and quantity required of each find number. Notes can be used to provide information like torque specifications or testing requirements. You may also want to include some reference dimensions for mounting features. We've given a lot of little details in this video, but we want to emphasize that your primary objective is to make drawings that are totally clear. We've posted a checklist to our website to help when reviewing a CAD drawing, but you should always do a final check by asking yourself, can a total stranger that knows nothing about my company or product look at this drawing and make exactly what I want without needing to call me?
A lot of new engineers really struggle with making drawings, especially because most universities do an awful job teaching the concept. With this video, we've tried to start you in the right direction, but ultimately, the only way to get better is practice. If you work at a company, your drawings will almost always be checked by an experienced designer or engineer, and that feedback is critical to improving your skills. We have more engineering videos coming soon, so be sure to subscribe so you don't miss them. Thanks for watching.
Yeah, okay. So these videos would tell you about the one that what we're gonna learn in half semester, yeah, in for 1 semester actually with the laboratory. So if you're still confused, that's fine, of course, because it's actually quite new. We're gonna learn one by one about that one. Yeah, okay, so don't worry, but this just tells you that what is engineering is about. Okay, and then let's watch another video about the another introduction. Maybe this would include with I think 6 minutes videos, yeah, about again from other point of view, yeah, about engineering drawing.
In this Easy Ed video lecture, we will learn what is engineering drawing, drawing instruments and its uses, and lines and types of lines. First, we will see what is engineering drawing. Engineering drawing is a type of technical drawing which is used to clearly define the requirements for engineered items such as views, dimensions, and necessary information. More than drawing pictures, it is also a language, a graphical language that communicates ideas and information from one mind to another. Most important, it communicates all needed information from the engineer who designed a part to the worker who will make it. Application of engineering drawing is used in ships, manufacturing, aerodynamics of automobiles, constructions, etc. Let us see different drawing instruments used in engineering drawing. In this we have a drawing board, drawing paper, pens, clips, or adhesive tapes, pencils, T-square, set square, scale, drafter, roller scale, protractor, French curves, compass, and eraser. Hey, it's time to concentrate now. Now let us describe each and every instrument. Drawing board is rectangular in shape and is made of wood about 25 mm thick. It is cleated at the back by 2 battens to prevent warping. The surface of the board should be smooth and it is used to keep the drawing paper. There is a working edge at the side of the drawing board. While selecting a drawing paper, we have to be sure that the size of the paper is smaller than the drawing board. To hold this drawing paper, we use pins or clips or adhesive tapes. Pencils are basically used to draw. The accuracy and appearance of a drawing depends on the quality of the pencils used. The grade of pencils, H, 2H, and HB are mostly used. Next is the T-square. It is made of 2 parts, the stock and the blade, which are joined together at right angles by means of screws and pins. T-square is fitted at the side of the drawing board and it slides along the edge of the board and is used to draw horizontal straight lines. Set square is triangular in shape with one of the angles as right angle. 2 forms of the set square are generally used. One having angles 45, 45 and 90 degree and the other is 30, 60, 90. Set square is a combination with T-square is used to draw lines at an angle. A scale is used to draw lines of specific length. Protractor is flat and semicircular in shape. Its circumferential edge is graduated to 1-degree divisions and is numbered at every 10-degree interval and is readable from both the ends. The protractor is used to draw or measure angles. The combination of a T-square, a set square, scales, and a protractor is a drafter. Its one end is clamped by means of a screw at the edge of the drawing board. The other end is adjustable. It has a scale which is at 90 degree and also has a protractor which can be rotated at certain angles. This scale can be moved anywhere we want within its limits. Next is a roller scale. It has a roller in it. It is used for drawing vertical lines, horizontal lines, parallel lines, angles and circles. Next instrument is the French curve. They are made in various shapes, one of which is shown here. French curve is used for drawing curves which cannot be drawn with a compass. It is used to draw curves like ellipse, parabola, hyperbola, etc. A compass is used to draw a circle of a specific radius and an arc at a specific distance. Soft Indian rubber is widely used to erase pencil drawings. The eraser should be such that it does not spoil the surface of the paper. Next we will see lines and types of lines. Just as in any textbook, we are taught to use the correct words for making correct sentences. Similarly, in engineering drawing, the details of various objects are drawn by different types of lines. Various types of lines are used in engineering drawing. Now let us see the different types of lines. First is a continuous thick line. This line is used to display outline and edges of the main drawing. Next is the continuous thin line. This line is basically used for dimension, extension, projection, leaders, hatching, etc. Next is a continuous thin freehand line. This line is used to show short break or irregular boundaries. Next is the continuous thin line with zigzags. This line is used to show long break. Next is the dashed line. This line is used to show hidden edges of the main object. Next is the chain thin line, long dash dotted. This line is used to represent the center line for circles and arcs. Next is the chain thin line with thick at the ends. This line is used to represent the location of a cutting plane. Let us take a quick review of what we've learned in this video lecture. First, we have seen that engineering drawing is a type of a technical drawing which is used to clearly define the requirements for engineered items such as views, dimensions, and necessary information. It is also called as graphical language and helps to communicate. Next, we have seen different drawing instruments used in engineering drawings such as drawing board, drawing paper, pins, clips or adhesive tapes, pencils, T-square, set square, scale, drafter, roller scale, protractor, French curves, compass and eraser and their uses. Finally, we have seen different types of lines used in engineering drawing to draw an object. So this is the overview of our video lecture.
Right, okay, so I think that should be enough, yeah. Those two videos, additional video for you to understand about, to describe about the engineering drawings, yeah. Of course, yeah, before I continue, any questions? Not yet? Okay. So, of course, the one that we show it here is, of course, a model, yeah, sebuah model. The reality should be more complex, and then to learn the complex one, and of course, because we're chemical engineers, we're not gonna think about those very complex problems, complex specimen that we watched in the first video. But the one that I would like to emphasize is we need to learn the idea, so we know the specimen, and then we can draw it to what is the front side and the maybe the sides and also the top sides, yeah, like that. Okay, now let's continue. So this one also the verbal communication. So using the verbal and written communication, the level of difficulty and the failure to communicate will increase, and also as the complexity of the products will increase. Okay, so let's watch, yeah. So this is an example complex, so let's read it. This one here. So drawing, the technical drawing, of course, is the graphical representation of the objects, and then the technical drawing is the knowledge and skills to represent complex technical ideas with sufficient precision for products to be mass produced. This is a very, very good emphasis, because and then the part would be easily interchanged as well. Okay, so for example, this one, yeah, this also, we called it split bronze brush journal bearings, yeah. This is the type of part, the spare parts, and then you can see that looks, it is very, very complex to about the drawing. Of course, you're not we're not gonna make this, yeah, but this is gonna some ideas that this is from the front view, very, very detailed, and then this is from the top view, and also this one is from the other sides. Okay. And then so in the next 7 weeks we're gonna learn step by step, for example, about the diameter, the dimension, how to draw a thread, how to draw the cylinder, and I'm just gonna give you the theory, and then for the practice you will have another session with the assistant from gambar technique, yeah, with all of them, and then using software, and then the software we're gonna use is SolidWorks, and the SolidWorks I think it should works on from Windows, yeah, Windows laptop, not the MacBook laptop, or maybe you can use MacBook, but you have to install another software something. Okay, this is also an example of a concrete 3D models, and sometimes also the important graphic is a virtual crash testing for crash worthiness. We just make a modeling, yeah. This is not the right one, but just to try to check that one. So back again about the technical graphics. So that the technical graphic would be the language used to first we know the visualization, yeah, and then the communication to refine and sketch and improve the aid, and now of course they are going to use CAD, yeah, computer aided design. For you, when you're still high school, before in high school, have you learned about CAD in school or not yet? Computer aided design.
I haven't missed.
Oh, okay. How about the others? Have you tried? No? Or maybe in some international schools, there should be, maybe, yeah. But anyway, so CAD software, for example, using SolidWorks, yeah, or others, or yeah, we can. It looks like, I would say, not like, yeah, very close to Minecraft or something, yeah, that try to sketch, and then from the sketch, they're gonna print out like that, yeah. And then, of course, with the documentation, the graphic is the most effective way to permanently record the design solution. And then the documentation drawing previously was 2-dimension detailed drawing, but now in SolidWorks, there are also 3D models as well, yeah. I'm not using SolidWorks for everyday job, but I saw my husband in a mechanical engineer. He's using these softwares, the SolidWorks softwares to for his work. Yeah. So for example, his work is actually he want to detect any defect, mau mengecek cacat, ya. He want to check any defect on the pipeline, on the chemical plant before the accident happened. So the way he do it is actually he modeled them, make the graphic, the technical drawing in the CAD, the computer aided design, in his laptop, and then try to model the pipeline, for example, similar with the real one, and they modeled them. For example, if I have this crack, kalau ada retakan sekian, how many days, ya, how long the pipeline can hold those oil inside the pipeline before it can broken or it can rupture, for example. So, and we can he can predict that, and then the company would be happy because, oh, okay, my life, the pipeline life is, for example, is only 5 years. So before 5 years, they have to schedule the changing of the pipeline. That is just example, and then he used that using computer aided design. Okay, this one also, of course, in the building, yeah. I think there would be a lot of software as well, if for you who likes doing building, or maybe similar with Minecraft. I have 3 boys and a girl, so those 3 boys and also the girl also love to play, I don't know, Minecraft something, yeah. So I think in a way it is good to build the sense of 3 dimension. That's the thing. Okay, this also, for example, for the 3D model for apartment, for example, yeah, that one there. And then this is, for example, another example about sketching. They want to make this penutup mobil, yeah, for the sun, to reduce the temperature inside your car, something like that. Okay, so this is a very old one. Yes, I think your assistant later on should be able to introduce you to the software about the SolidWorks, and you're not. I think there should be some freehand drawing tugas, yeah, assignments in the next few weeks, but then also a lot of laboratory drawing using SolidWorks. Okay, so this is a example of 3D models, very quite long time as well. Okay, now so the convention, again, the ruler, the rules, the peraturan, yeah, the convention, the standard. Engineers would be always follow standard. For example, chemical engineering ITB and other several programs in ITB is internationally accredited in the US by ABET, Accreditation Board of Engineering Education. And when the American team visited ITB 5 years ago, they asked about is your students familiar with standard? So standard for engineers is really important, because it is actually allow us when we graduate and then we work somewhere outside worldwide, we can understand and then we can mapping the standard. Yeah. So the commonly accepted practice, rules and method, for example, the dash line multi-view is actually to design it for a feature hidden, yeah, in the current viewpoints. Of course, so in any standard, the hidden line, the dash line, tells you about the hidden line. Okay. For example, now the convention, the center point, yeah, in the for the circle, the titik pusat, the center point would be always looks like this. Okay, and then the standard is actually a set rules that govern how technical drawing are represented. For example, for United States, if you're using ANSI, blah blah blah, drawing side, sheet size and format, and also there's align convention and lettering, multi-view and sectional view, and also there's another one standard, ISO, International Standard Organization, or JIS, Japanese standard, or maybe SNE. Yeah, we can't get that one as well. Okay, so this one we're gonna learn each of these blocks, yeah, the box later on. So just be patient. In a few weeks, in every week we're gonna learn one by one about, for example, about the dimensioning first, about the manufacturing first, and then how to draw 2-dimension and 3-dimension and so on. Okay, so now the last one is about design. Yeah, so so the engineering drawing is one part of a design. And design is the process of conceiving and reinventing ideas and communicating those ideas to others in a form of that is understood easily. And then after that, there's a process of iteration. If you want to design something, okay, for example, okay, what is the diameter of this pipeline, and then the pipeline will accommodate, for example, 1,000 liter per hour of oil. If you only just measure, it is not design, it is only calculating, yeah, calculating the diameter. But the design, there should be an iteration proses yang berulang kali. So you conceive the idea, buat idenya, and then you have to communicate it with the other part counterpart, and then maybe recheck again, redo again, and so on. So you as a chemical engineer, as a designer later on, don't worry if your work, if your design have to be remodeled, you have to redo again, because the design required feedback. Yeah. So for the product and process development, the design here, there is a functional engineering design and also the aesthetic, yeah, the industrial design, and it's actually included in engineering design cycle, and it comprised of a product and also processes. Yeah, this is an abstract design. Yeah, of course we don't know the functionality, but for aesthetic also, we want to see it should be nice. Yeah, it should be looks good. Okay. But the functional design means that concern with the function of the product and process. So, for example, this very old car, it should withstand with the crashworthiness, harus bisa aman kalau ketabrak. Yeah. So we as engineer, of course, will concern with the functional elements. Okay. So the many products will have both aesthetic and functional design elements, and then require engineers and designers to work as a team to produce a product or system that is both functional and aesthetically pleasing. Now, ITB is also toward multidiscipline programs. For example, some the ones from mechanical engineering collaborate with the students from product design, so they can have a product that also functional but also aesthetically sounds, yeah, very nice to see as well. Okay, so engineering design process is normally associated with the entire business enterprise. So we started with the input, what we want, we need the material, the capital, the energy, the time, yeah, and then also the social concern, the customer need. What is customer need? Yeah, especially when at this time, the time for online shopping. Yeah, you can see that so many products in Tokopedia or Shopee and Lazada and so on. Yeah, and then innovation it always happens. Yeah, and then for the process, it comprises of designing, planning, producing, constructing, and also financing document, and then we can get the output as a product system structure for various markets. Yeah. Okay, so the engineering design will comprise. So first is a problem identification, and then you have the ideas. Okay, I want to make this one. Let me give you an example about what I don't know. Yeah, maybe I have something here. Maybe for example, this is toy from my kids. Yeah, this one is transformer. Yeah, for example, they want to make the transformer toys that can transform into cars, for example. Yeah, so I don't know. I think this is engineering design. I think, okay, because you have the problem. So for example, the problem, we want a toy that can transform from car into the robot. I don't know how to transform this into the car, but anyway, yeah, this is the robot, but it can transform into the car by changing something. Yeah, I don't know how to change that. Anyway, just leave it like that, and then once you get the idea, you can get the design, and after that you can have analysis. For example, it is easy to open, it is easy to transform something, and then this will have a lot of loop iteration. We call it iteration, or uji coba lagi. Yeah, this is to define your design, and then once you have the optimized, then you can document it, and then you will have a product that is good and is functional and then is aesthetically, and then for example these toys, it gonna make the kids happy because they can continuously change between the the robots and then change it into the cars, and then the robots into the cars again, and then like endless time. Like for example, this toys is also, I think it's been 5 or 6 years, yeah. And then it is from Hasbro, and then we can see the quality is very good, so it doesn't chop or broken or something, yeah. So if you compare it with for example, with the very less expensive toys, you can compare it. Okay, so if I want to design maybe very cheap toys, maybe only 20.000 rupiah or something, but in one day or 1 week it's gonna broken. But if for example that I want to design a very sturdy and then a good piece of transformer, maybe around 400.000 rupiah or something, yeah, with the good material, then you can get the outcome you want, yeah. So the problem identification, the constraint, any project that you gonna do later on, yeah, not in this class of course, it's based on the problem specification, and then once you optimize them, you can do the documentation. Okay, so it actually okay, so start from the ideation ideas. You identify the problems first. For example, I want to make a good toys which is should be long term, not easy to broke. So okay, so I have to choose the material, yeah, the type of material, polyethylene or something, yeah, that is very good. And then the design, yeah, how they change this one, the robots, and then the design, and then after that you refine them, of course with the 3D model. You model them, design, analysis, maybe checking with the impact test, and then try to manufacturing. Is it easy to manufacture? Is it difficult, or is it very complex, or is it doable to be manufactured? And once you get that, then you do the implementation by financing with the marketing, and then the production, and then planning and documenting. Yeah. So back again from the technical drawing, it actually included in around this one, the idea and the 3D model. So how you can get the 3D model that is can be implemented by others, and can be manufacturing by others. Okay. For example, maybe this one, it is actually maybe designed in the US, for example, but the manufacturing plant is in China or in Indonesia. So the workers, the plants in China or in Indonesia must know how to produce this one, even though the designer is in the US. Okay, so I think that concludes the slide for today. So in this first day of the semester, so again, I'm again welcome you again to Bandung, to ITB. So I really hope you have a very good academic experience. The one that make you difference between study in ITB, study in UGM, or in UI, or even in Australia, or in others, yeah, is actually the one that makes different is the academic atmosphere. Yeah, maybe when you be more in campus, you will have also the academic atmosphere with your friends as well. Yeah. All right. So again, I welcome you to the campus, and then I hope, even though we are not seeing you in the class, I hope you can have an enjoyable experience for this second semester. And don't forget, 2 SKS, 2 credits means around 6 hours per week. So you have to spend enough time to understand this. Okay, looks like this internet signal tells me to finish the course. So before we finish, any questions regarding, I don't know, CX, EduNext or something? No? All right then. So I'm sure some of you are listening like while traveling, but I hope this is just because you're still preparing for your semester. I really do hope that next time you watch the you attend the lecture, please make yourself comfortable, yeah, to understand the yeah, have a coffee before or have a good lunch before, yeah, so you can prepare and then listening to my lecture, especially because next week we're gonna go to the more details. All right, I'm gonna stop the recording now.